Assalamu alaikum and greetings. The text of our next task is as following. Inside infinitely long conductor shown on picture here, where magnetic permeability of this conductor is approximately the same as magnetic permeability of air, with the circle cross section with radius A shown on picture, a constant current flows, so we have a constant current here, considering that the current is uniform through all the cross sections, so it means that all of our charges are uniform through this cross section. Our current is uniform through this cross section. That means that our current density is the same for every cross section. It is a constant, and it is equal total current divided with the total surface of this cross section of conductor. We need to determine magnetic flux density inside a conductor and outside, and draw its function from the radius. So firstly, what we need to do is I will draw here a cross section of our conductor, which is a circle. So, and our conductor has a radius A. And now we need to calculate a magnetic flux density inside a circle as a function from radius r or distance r. Our current has this direction, which means we are looking at it from above. Also we need a vector of this infinitely small surface normal ds, and we will take the same direction as the current. And in order to calculate magnetic field, we will use Ampere's law, because we need to calculate our magnetic field B as a function from R inside a conductor. We cannot use sum of current to say the total current is I. We could use that if we were analyzing outside a conductor, and that will be our second case. But because we need as a function from R, we must use this formula. So what does our Ampere's law says? It firstly says close the contour where we want to calculate the magnetic field. So this is, we want inside as a function of R, so I draw it for some case. We need to determine the B, the direction, and DL. It is determined with the right hand rule. Current goes towards you, which means this is B direction, and this is also because L total length is this will be the L that has the same direction as B. We have also the direction of our current density J and the direction of ds, which is the same, which means the dot product of these two vectors is the same, and we need. So now we need to calculate it. What will we get? We will get that inside this is B times dl, or a closed contour, which is equal to mu0 integral the current density times ds over surface S. Now B is a constant at this radius, it has the same value, so we can put it in front of integral, and we will get integral of dl, which is only L, which is total length of our closed contour. So this is our closed contour length. What is length? Actually, it is a length of this circle, and it is 2 radius times p. What is the radius here? We took that the radius is r, small r. mu0 times also, because in the text of task it said that the current is uniform, which means if the current is uniform, our flux density is constant, and it is equal to the I divided with the total surface of conductor. Very important, of complete conductor. So we can also put it in front of our integral, and we will get integral of ds. But what surface are we looking at? Well, we are looking the surface which is created with our closed contour. This is our closed contour, which means this is the surface created with its own contour. So, here we will get Rp mu0. Current density, because the current is uniform, we can write it as a total current I divided with the total surface of cross-section of conductor. Total surface, this of conductor, is not this. This is what we want to calculate using Ampere's law at this distance, what is magnetic field value, etc. No, we need the total surface of conductor. And total surface of conductor, because the conductor cross-section is circle, and it is radius squared times p. So we will write that here. Integral ds is only s surface, but which surface? This surface created by our closed contour, which is mu0 I r square p times. So excuse me, here j is a square p, because it is the surface of conductor, as I already told you, times s surface of this is, once again, it's a circle, it is l square p. So we can this and this, and from here we will get that our b is equal mu0 I r, and r square will be shortened pp, we will get mu0 I times r divided with 2p a square. Let me just check. Tesla, and this is inside of conductor. If we want to calculate it outside of conductor, so we will choose our closed contour outside of conductor with new radius r. And what will we get? Well, we will get the same result, b times l, but in this case l is this, 2r pi, the distance, the radius, which is equal mu0 times, now we can use this formula, sum of I. Why? Because our closed contour is above, it takes in consideration of total surface of our conductor, total current. So we can choose what current is inside our closed contour. Well, it is a total current I. We don't need to use current density, because here our total current I, and because it is uniform, it's inside. So we write it that outside is mu0 I 2r. So what did we get? We need now to draw as a function. Well, inside a conductor, we got that our b is equal mu0, which is constant, I, which is constant, 2p a square, which is constant, times r. So these are some constants, and we get that b is c times r. So it is a function of r, which means that it is the same. How does y equals some constant times x looks like? Well, we say it's a straight line. This is y, x, y times q times x. It is a straight line. We say this is the same. Just now we will write and analyze b as a function of r, as a function of distance, which means inside a conductor, so inside a conductor r, this is for r equals a, that's the point. Inside a conductor, for r equals 0, our magnetic field density starts from 0 and grows with the straight line linearly up to the this border. And then after a conductor, we have the formula now. Magnetic field changes with some other law. What do we have here? Well, we have here mu0 I 2 pi r are a constant. I will say C prime times 1 divided with r. This is the same function as we had q times 1 over x. And this is not also linear only like this. No, that is not the case. This is epsilon equals minus x. Most students make a mistake here. This function is actually like this. So, from this point, here our conductor ends, and as we are moving away from our conductor, our magnetic field density changes with this law, which means it has this type. So this is our magnetic field inside conductor. It rises linearly, it decreases linearly, but as a function some constant times r, but here it is some other constant times 1 divided with r. It decreases with this law as we move away from a conductor. Because of this, so as we move away from a conductor, there are some standards which say those two conductors must be on a distance from human at that and that distance, but very thankfully the conductor magnetic field changes with this, it changes very fast. So thank you for watching this video, see you in the next video.